English at all because of COVID-19. So maybe my tongue doesn't work well, but sorry about that. Anyway, so today I talk about a singularity from the perspective of geometric perspective. And so in the first talk, I quickly review the definition and basic property of F singularity, especially F pair rings and F regular rings. So then my ring are maybe this is always Natalian. Oh, sorry, it's maybe I should have a Natalian domain. For simplicity, let me assume a ring is domain of characteristic P, positive characteristic. And E is a positive integer. I consider P to the E is root of R, which is a set element X. X is in the algebraic closure of fractional field of R, algebraic closure of fractional field of R, such that X to the P to the E is contained in R. So this is a ring which contains R, and identify so natural inclusion from R to P to the is root of R with E times Frobenius map, which sending X to the P to the E. Yeah, because we can do this because sorry, it's something. Because so this is E times Frobenius map, and this is natural inclusion. So, but we have isomorphism because X goes to X to the P to the E, and this is identity, so X goes to X, and this is natural inclusion, so X goes to X, but X is P to the is root of X to the P to the E. As yes, so we have this kind of commutative diagram. So therefore, we identify the natural inclusion with E times Frobenius map, and we say R is F finite. If P's root of R is a finitely generated R module. And so let me give an example of F finite rings. For example, first, so let me consider the case where R is a field. So K is a field. In this case, K is F finite if and only if extension degree is finite. So that is easy. So in particular, K is perfect. If K is perfect, then it's F finite. So perfect field is F finite. Perfect field K, which means P of K is equal to K. It's F finite. Second example is a little bit more complex. So let me assume K is a finite field. And I consider a ring essentially of finite type over K, which means ring is, so we can write as follows. So R is equal to the quotient of polynomial ring over K, and we consider its localization. P is a prime of this quotient ring. So this ring is also a finite. The third example is a complete case, which means if local ring is a complete local ring, so with a residue field a finite, then R is a finite. So basically, in algebra geometric settings, almost all rings are a finite in positive characteristic. So from now on, let me assume. So from now on, let me assume all rings are a finite. I mean, all rings of positive characteristic is a finite. So later, I consider rings in characteristic 0. So, but if we work in positive characteristic, so always I assume ring is a finite. Okay, and sorry, let me give one more remark. So this is due to Kuntz. A finiteness implies excellent. So our rings are automatically excellent because of this. Okay. Okay, now, so let me introduce another result of Kuntz. So this is a starting point of the theory of F-singularity. So if ring is regular, sorry, ring is regular if and only if Frobenius map is flat. So, but in our situation, P root of R is locally free over R because we are assuming our rings are F finite. And this is equivalent to for any E, P to the E root of R is locally free. So we have a characterization of regular rings in terms of Frobenius or P root of R. And so, okay, so let me give an example. I think the easiest example is a polynomial ring. Sorry, I got a question, so let me.
Says, is R local in your?
No, at the moment, R is not necessarily local, so that's why I said locally free.
Okay. Okay.
Yeah, thank you. So first example is maybe most easiest example is a polynomial ring, and one-dimensional polynomial ring. And let me assume K is perfect. In this case, P root of R is nothing but a polynomial ring, but the variable is P root of X. And this guy, so we have a following decomposition, like yeah, and finally kx times x p minus 1 over p. So, uh, so we have this kind of decomposition. So this is free R module of rank p. So yeah, of course, so polynomial ring is regular and Kuntz-Selm set, so regular ring. So for regular rings of p power over R is locally free, and indeed in the case of polynomial rings, so p root of R is actually free. Okay. Then now let me introduce two classes of F singularities. First singularity is F pure. R is F pure. Or since I'm assuming rings are F finite, so which is equivalent to the locally F split. Yeah, we say R is F pure if natural inclusion from R to P root of R, this splits as an R linear map. And this is equivalent to saying that for any or for some E, sorry, maybe let me move to another node. So this is equivalent to for any or some E, natural inclusion from R to the P to the E's root of R, this map splits as an R linear map. So yeah, and maybe I should have said the meaning of splitting. So splitting means there exists a phi R linear map from P's root of R to R, such that composition with this natural inclusion, this composition map is identity on R. So this is the meaning of splitting. Yeah, I guess Indian people basically very familiar with Frobenius splitting. So I don't explain the detail, but anyway. So then next, let me introduce another class of F singularity called strongly F regular. So, but in this talk, let me simply say F regular. R is F regular. Yeah, we say ring is F regular if for any non-zero element C. I'm assuming R is a domain. For any non-zero element C, there exists an integer E such that first I consider natural inclusion from R to the P to the E's root of R, and now I consider multiplication map by P to the east root of C. This composition map splits. So which means this map X, this map sending X to X and to P to the east root of C times X. Yeah, this map splits as R linear map. So this is a definition of F regularity. And so easiest remark is F regularity implies F purity. Yeah, just take in the definition of F regularity, take C to be 1. So then you get the definition of F purity. Okay, then and so let me explain basic property of F regular rings. First of all, I should say, so regular ring is F regular. So, but this is just an easy consequence of Kuntz's characterization of regular ring. So proof is easy. Let me explain the proof. Fix non-zero element C in R and choose sufficiently large E such that C is not contained in P to the M to the bracket P to the E. Sorry, I should have said so. Here I assume, sorry. Here I assume Rm is local. Assume Rm is local, sorry. Strong F regularity is preserved under taking localization. So let me assume ring is regular. R is ring is local. So let me assume Rm is local ring. Then fix non-zero element C in R and choose sufficiently large E such that C is not contained in the Frobenius power of M. I guess everybody knows the definition of Frobenius power of ideals. So then, yeah, and by Kull's intersection theorem, we can take such E. And but this condition is equivalent to saying that P to the east root of C is not contained in M times P to the east root of R. And by Kuntz's result, we know P to the east root of R is free. Free as R module. Then by Nakayama, since P to the east root of C is not contained in the extension of maximal ideal, so by Nakayama, P to the east root of C is a part of a free basis. Of this free module. Then, yeah, consider a free basis of P to the east root of R. We can take a map phi from P to the east root of R to R, sending p to the is root of c to 1 because this guy is a part of free basis. But this means since C is an arbitrary non-zero element, so this is the definition of F-regularity. So regular rings are F-regular. Okay. Now, okay. I think second important property is again, F-regularity implies normality. This is also easy, so let me give a proof. Assume x over y is an element of fractional field of R, which is integral over R. Then t is R bracket x over y. So this ring is a finite extension of R. So this is just a definition of being integral. So then there exists a non-zero element C in R such that C times T is contained in R because this extension is finite. In particular, C times x over y to the p to the e is contained in R for any e. And this means C times x to the p to the e is contained in the ideal generated by, y to the p to the e in R. Y to the p to the e, yes. Now, since we are assuming ring is F-regular, since R is F-regular, there exists a R linear homomorphism phi sending p to the east root of c to 1. There exists some e, some integer e, and there exists some R linear map phi sending p to the east root of c to 1. Then, so x is equal to phi of p to the east root of c times x. This is a definition of phi. But since c times x to the p to the e is contained in the ideal generated by y to the p to the e, therefore, this guy is contained in y times p to the east root of r. Sorry, I should have said right. This condition is equivalent to p to the east root of c times x is contained in y times p to the east root of r. Sorry. So this condition is equivalent to this condition. So therefore, we have a discontainment. But since phi is R linear, so this guy is contained in the ideal generated by y. So x is contained in the ideal generated by y, which means x over y is an element of R. So maybe, yeah. So x over y is an element of R. So R is normal. R is integrally closed. Okay. And so let me explain one more basic property of F-regular rings. Now Cohen-Macaulay property. F-regular rings are Cohen-Macaulay. Yeah, this is because, so yeah, proof is again easy. So let me explain the proof. Well, first, since I'm assuming a finiteness, the ring is excellent. In particular, non-Cohen-Macaulay locus is closed. So, I mean, considering a generic, so yeah, looking at the generic point of non-Cohen-Macaulay locus, we may assume Rm is local and Rp is Cohen-Macaulay for any p not equal to maximal ideal. Yeah, we can reduce to this case. But then local cohomology module, so lower local cohomology modules are so have a finite length. For any I less than D is the dimension of R. So then yeah, we take non-zero element C in R such that C kills all lower local cohomology modules, which means C times HIMR is equal to 0 for any I less than dimension. Yeah, we can take such C because HIMR has finite length. But since R is F regular, there exists an integer E and the composition map of natural inclusion from R to the P to the eth root of R with multiplication by P to the eth root of C. This composition map splits by the definition of F regularity. Then taking local cohomology functor, so this map is injective. This map is injective, and here the multiplication by P to the eth root of C. But Yeah. So we consider this multiplication map, but basically this is the same thing considering a multiplication map by C. Yeah, because we have this commutative diagram. Yes. So this is the same thing, but by the definition of C kills local cohomology module. So multiplication map by C, this is zero map. So then, yeah, which is equivalent to this multiplication map is also zero map. This is also zero map. But and but this so this map between local cohomology module is injective because of F regularity. But multiplication map by P to the root of C is zero map, which means local cohomology should be zero for any I less than D, which means ring is Koema-Kore. So that is a proof. Is it okay?
Yes.
Okay. So then, basically, at the moment, so we have seen regularity implies F regular, and F regular implies normal and Koema-Kore. And F regularity also implies F purity. Yes. And so now I want to give a couple of examples, but so in order to do so, I need a Fedder's criterion. So now let me explain Fedder's criterion. So ring is regular local ring of positive characteristic. Again, I'm assuming a finiteness. And for simplicity, I assume I is a prime ideal. So then the quotient ring R over I is F pure if and only if I to the bracket P colon I, yeah, this is the colon ideal. Sorry, my maximal ideal is M. This colon ideal is not contained in M2 bracket P. And second, I consider J, ideal J. This is a radical ideal of R, and which contains J such that J over I is a defining ideal of the singular locus of R over I. So this is the definition of J. Then the quotient ring R over I is F regular. if and only if there exists an integer e such that j times I to the bracket p to the e colon I is not contained in m to the bracket p to the e. M to the bracket p to the e. Yeah. And in particular, if I is a principal ideal, so which means the quotient ring is hypersurface, in that case, first condition is equivalent to saying that f to the p minus 1 is not contained in m to the bracket p. And the second condition is equivalent to there exists an integer e such that j times f to the p to the e minus 1 is not contained in, so is not contained in m to the bracket p to the e. This is very useful criteria. And now I'll show you concrete example. Then my R is the localization of three-dimensional polynomial ring, like this. And the first example is f is equal to x cubed plus y cubed plus z cubed, and I assume characteristic is not equal to 3. In that case, yeah, using Jacobian criteria, we can see in this case J is a maximal ideal. And first, we consider the case where P is equivalent to 1, congruent to 1 modulo 3. In this case, expansion of f to the p minus 1 is equal to so we consider polynomial quotient. This, then this quotient times x to p minus 1, y to the p minus 1, z to the p minus 1, plus something, plus g, but g is in the ideal generated by xp, yp, zp. And this quotient is non-zero. So therefore, by Fedor's criteria, therefore, f to the p minus 1 is not contained in ideal generated by xp, yp, zp. So by Fedor's criteria, R over F is F pure. And but if you consider J times F to P minus 1, then this guy is contained in the ideal generated by xp, yp, zp. Yeah, because of this, because of this expression. And similarly, yeah, we can check for any E, J times F to the P to the E minus 1 is contained, which is, this guy is contained in the either generated by X to the P to the E, Y to the P to the E, Z to the P to the E. So this means R over F is not F regular. Okay, so then, and now I consider the case where P congruent to 2 modulo 3. In this case, we look at F to the P minus 2. So F to the P minus 2, then this guy can be written as so first, so we consider polynomial coefficient like P to the 2 choose P to the 2 over 3, sorry, P minus 2 over 3, P minus 2 over 3. Yeah, we consider this polynomial coefficient and x to the P minus 2, y to the P minus 2, z to the P minus 2, plus something, and again, something is in either generated by x to the either generated by xp, yp, zp. And this quotient is non-zero. So then f to the p minus 1 then has to be in from this description, f to the p minus 1 has to be in either generated by xp, yp, zp. So R over F is not F pure. So yeah, like this, F singularity heavily depends on characteristic. And the second example is, sorry, this is first example. And the second example is actually so easier one. So I mean, f is equal to x squared plus y squared plus z squared, and p is not equal to 2. In this case, again by Jacobian criteria, so our j is nothing but maximal ideal. And f to the p minus 1, we look at f to the p minus 1, then so this is equal to the now binomial coefficient, so p minus 1 choose p minus 1 over 2 times x to the p minus 1, y to the p minus 1, plus g. G is contained in x to the p. G is contained in the ideal generated by xp, yp, and z square. Yeah, we can write like this. Then f to the p minus 1 times z, this guy is, of course, this quotient is non-zero, and this guy is equal to x to the p minus 1, y to the p minus 1 times z plus g times z, but this is not contained in the either generated by xp, yp, zp. So, and z is the element of j. So by Fedor's criterion, R over F is F regular. So using Fedor's criterion, we can check F regularity or F purity. But in a concrete example, So we have to compute binomial or trinomial or quotient. So that is not so easy in general. Yeah, anyway, so this is an example. So, until now, I quickly reviewed the basic property of F-regular and F-pair rings. And now let me switch to the situation in characteristic zero. I want to discuss a singularity in characteristic zero. So now my ring R is normal domain, essentially of finite type over C. So which means my ring is something like this. It's a quotient of polynomial ring, and take localization. And I need to assume, in addition, I need to assume R is Q-Gorenstein. So this means canonical module. So I consider class of canonical module in the class group, divisor class group. So this class has a finite order. Yeah, which means more, which means, okay, let's consider ideal isomorphic to omega. Oh, sorry, let me assume normal local domain. R is a normal local domain, essentially of finite type. Okay, and I consider ideal I, which is isomorphic to omega R. Then there exists an integer R, and this is R's symbolic power of I. This is a principal ideal. This is R's symbolic power. This is the definition of Q-Gorenstein condition. And I need this condition because, okay, but just, let me give one remark. Gorenstein condition, of course, implies Q-Gorenstein. Yes. Yeah, being Gorenstein implies being Q-Gorenstein. So this is obvious, but converse does not hold. For example, let's consider two-dimensional polynomial ring and consider third Veronese, which is a ring generated by x cube, x square y, xy square, y cube. This is Q-Gorenstein, but not Gorenstein. Okay, then, yeah, I assume ring is Q-Gorenstein. In that case, yeah, I don't give a precise definition, but so using a resolution of singularity, of x is a spec of R. Yes. X is a spec of R. Using a resolution of singularity of spec R, we can define some numerical invariant. numerical invariant, so-called minimal log discrepancy. So whose value is a non-negative real number or minus infinity. So this is a minimal log discrepancy. Yeah, I don't get the definition of minimal log discrepancy, but roughly speaking, so first we consider resolution of singularity, which is y project of least link RJT sum j. J is the ideal of J is the sum ideal of R such that Y is regular. And in that case, yeah, this is just very rough explanation. So first we take such Y, then so minimal log discrepancy measures measure the difference between omega. Yeah, it's a very rough speaking, but omega R J T, and we consider R symbolic power. So this R is sorry. Yeah, this R is this R, and we consider R symbolic power of graded canonical module of least link, and R symbolic power of omega R. Yeah, it's a not precise definition, but something like this. And okay. Now, yeah, using MLD, we can define the singularity in characteristic zero. So we say R is KLT. KLT is an abbreviation of Kawamata log terminal. Kawamata log terminal. If minimal log discrepancy is greater than 0. And we say R is log canonical if minimal log discrepancy of x is spec of R is greater than or equal to 0. Yeah. Anyway, so let me show you example. So then maybe you can get some feeling about KLT or log canonical singularity. Okay, the first example is I consider the quotient of three-dimensional polynomial ring by x to the a, y to the b, z to the c, and take its localization. And I assume a and b and c is greater than or equal to 2. In that case, R is KLT if and only if 1 over a plus 1 over b plus 1 over c is greater than 1. And R is log canonical if and only if this number is greater than 1 or equal to 1. So in particular, previous example, where, yeah, for example, if you consider this equation in characteristic 0, then this is log canonical, but not KLT, because 1/3 plus 1/3 plus 1/3 is equal to 1. And if you think of this equation in characteristic 0, if you consider this equation in characteristic 0, then this is KLT, yeah, because 1/2 plus 1/2 plus 1/2 is 3/2 is greater than 1. So this is KLT. And sorry, I consume almost all time. So, but let me give one more example. So that okay. Yeah, let me give one more example. Maybe two, but anyway. Let me consider two-dimensional case. The two-dimensional KLT singularity. So we have a complete characterization. So, I mean, R is KLT if and only if there exists a smooth affine domain S over C, and there exists a finite group acting on S, and exists a maximal ideal of SG. SG is an invariant subring, so this is an invariant subring of S. This is M is a maximal ideal. Then such that the completion of R is isomorphic to the localization of SG with respect to M, and we take completion. So basically, so this kind of singularity is called quotient singularity. And in dimension 2, KLT singularity is equivalent to quotient singularity. And so, sorry, let me give one more example. Yeah, log canonical singularity is a little bit more complicated even in dimension 2, but let me give one example. I consider hypersurface, two-dimensional hypersurface, and yeah, let me make it local. And F is a homogeneous polynomial of degree 3, such that, yeah, Jacobian ideal with respect to J and take radical, then the radical of Jacobian ideal is equal to maximal ideal. So this means a quotient ring. I mean, sorry, how should I say? Maybe, yeah, this is not good way to just yeah, just sorry, radical of Jacobian ideal is equal to maximal ideal. Okay. So then in this case, then R is log canonical. So for example, F is is equal to x squared plus y squared plus z squared plus xyz. Yeah, this kind of equation is log canonical. And so sorry, maybe it's time to stop. So then in the next talk, I want to explain the relation between the singularity in characteristic 0 and F singularity, and we use reduction technique. And if I have a time, I want to explain the application of F singularity theory to birational geometry. So can I stop here?
Yes, we can take some questions.
Uh-huh.
Are there any questions?
Sorry, maybe it was too easy.
I have a question. Am I audible?
Yes.
So, in the proof of F regularity implies Cohen-Macaulay, the first statement was, since non-Cohen-Macaulay locus is closed, we may assume that RP is Cohen-Macaulay for P not equal to the maximal ideal. Can you explain the statement, since non-Cohen-Macaulay locus is closed?
Oh, okay, yeah, because okay, then so let me denote by W. W is a non-Cohen-Macaulay locus. So then, since this is closed, there exists an ideal I such that W is equal to Vi, and I take Q. Sorry, take Q as a minimal prime containing I, and consider the ring RQ. So then it's a okay. The fourth, I mean, let me assume W is non-empty. Otherwise, yeah. Let me assume W is non-empty. So then, yeah, we can take such I and take Q, so which is a minimal prime containing I. Then consider the local ring RQ. So then this is non-Cohen-Macaulay, but RP is Cohen-Macaulay for any P in any P containing any P which is contained in Q, because I is defining idea of non-Cohen-Macaulay locus, and so P is not contained in. So sorry, P does not contain I. Therefore, RP should be Cohen-Macaulay. So then,
I guess I meant to ask if is non-Cohen-Macaulay locus is closed. Is that because we are assuming excellence condition? Is it
oh
a
yes,
result?
exactly, yes.
Yeah. Okay.
Yeah.
Yeah. Thank you.
Sorry. Yeah, because our ring is F finite, and F finite condition implies excellent. So then I assume, yeah, we can use excellent condition. Sorry.
There is a question from Mitra Kole. Is the definition of KLT singularity is MLD bigger than -1?
Yeah. Sorry, it's a little bit confusing. So, where is the definition? It's yeah, because so birational geometer used to use a invariant called minimal discrepancy, but now people use a minimal log discrepancy, and the minimal log discrepancy is just a minimal discrepancy plus 1. So if you use minimal discrepancy, the KLT condition is equivalent to saying the minimal discrepancy is greater than -1.
Okay. I have a question about is the locus of these singularities. Can we determine the defining ideal of the locus of F regular and F pure singularities?
Mm-hmm. Yeah. It's I don't. Yeah. Yeah. In this talks, I don't define, but so we can define test ideal tau r and non-FPR ideal sigma r. Then basically tau r defines non-F regular locus, and sigma r defines non-FPR locus, and under yeah, basically, if you assume a finiteness condition, these ideas are compatible undertaking localization.
Okay. So in principle, we can calculate them for hypersurfaces.
Yes, in principle, but maybe yeah. Yeah, if you use Macaulay too, yeah, actually you can compute it, I think.
Okay. But they may depend on the characteristic, I suppose.
Oh yes, of course. It depends on characteristic. For example, yeah, as I mentioned before, it's a yeah. In this case, f is equal to x cubed plus y cubed plus z cubed. In this case, it depends on congruency class. So just a modulo 3. It's a kind of it's a beautiful behavior. But but if you think of this guy, if you think of this guy, then it is difficult, at least by hand, to check which characteristic quotient ring is FPR and which characteristics the quotient ring is not FPR. So then, yeah, it does not depend on congruency class.
I see. I see. So what you introduce in characteristic 0, you introduce these singularities, and characteristic P also you introduced two singularities. What is the connection?
So what is, sorry, could you say again?
What is the connection between them?
Oh yeah, basically, yeah, next talk I will explain, but F regularity, oh, sorry, something wrong here. Yeah, F regularity correspond to K-T condition, and F purity correspond to log canonical condition. So if we want to study K-T singularity using this correspondence, so it is enough to study the property of F regular rings in principle. Of course, there's some exception, but we have a correspondence. So in order to study geometric singularity, we can use commutative algebra in positive characteristic.
Okay. Any other questions? Okay, in that case, thank you, Shunsuke, for your talk. we